Good morning. Lesson 2 is key features of exponential functions. So we practiced just working with exponents in lesson 1, just to kind of gear us up for the next couple of lessons. Lesson 2, we're going to be talking about graphing exponential functions, and then lesson 3 is kind of applying exponential functions. So our learning targets, I can recognize key features of exponential functions. And in your activity, I actually broke that down into each of the individual key features. So a really important thing is that an exponential function does not simply have an exponent. So like x to the second, that's a quadratic. That is not an exponential function. And it's only an exponential function if the exponent is the variable. So this is the form that they are in. Y equals a times b to the x. A and b are numbers. X and y are the variables. So it's an exponential function if the variable is in the exponent. A is what we call the initial value. So if you start with like $10, and it's exponential if you keep multiplying it by the same amount. So there's a famous problem: would you rather $1 million, or for 1 month, on the first day you get a penny, and on the second day we double that and you get 2 cents, and on the third day we double that, so you get 4 cents, and then 8. So you keep multiplying by the same number each time. A is the initial value, or sometimes we call it the starting value. It's how much of something is at the beginning. B is either called a growth or a decay factor. And it's going to be important here later that you keep in mind that the number in the equation, the number that has the exponent, is a growth or decay factor. There is also a rate that is kind of directly tied to it, but it's a little bit different. So exponential graphs only have 2 shapes. I mean, it's the same shape, but it has this kind of nice curve. So one side flattens out. This would not keep going down forever. This would flatten out and look almost horizontal. It is getting smaller and smaller, but you can't see it with the eye. So one side flattens out and keeps getting smaller, and then the other side keeps getting steeper and steeper. And that is the curve of an exponential function. If your function is growing, if it's growth, then it's going, as you move from left to right, it's increasing, 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 increasing. And this happens if your growth factor, if your b is greater than 1. So if your b is some number greater than 1, then your function is going to increase. So that's like the penny problem. You're doubling it, you're multiplying by 2, multiplying by 2. So your number would just, the money that you get would just keep getting bigger and bigger and bigger, faster and faster. Exponential decay means that something is decaying, or you're getting less and less of something. So maybe the high school has rats, and we put out rat poisoning, and then we're going to kill them. So there's fewer and fewer and fewer and fewer rats, right? So this side actually would come from way up here, pretty steep, and then this side would flatten down. It's not going to keep coming down here because we're not going to have negative rats. It's going to flatten out. And that happens if your b, your factor, is between 0 and 1. It's not going to be less than 0. It's not going to be negative. So like if b was 1/2, that would mean that each time we put poisoning out, it would kill half of the rats. We'd only have half as many. There's something else I was going to say, and I don't know. It'll come to me. Sometimes I think there's problems in Delta where or maybe it's in Desmos. Somewhere there are problems where you just have to say if it's growth or decay based on the equation. So let's look at that before we even try to graph these. We're going to graph these exponential functions. We're going to plot at least 3 points. So we're going to start with the starting or initial value, and then we'll put a positive and a negative in for x. So for this one, I'm going to start out by rewriting it because as it looks right now, you don't really see that there is an a and a b. Remember, your exponential function is a times b to the x. A is how much of something you start with, and b is what you're multiplying by repeatedly. X is how many times. So right now, this doesn't have an a in front. There's nothing being multiplied in front, but I can rewrite it. F of x equals 1 times 2 to the x, because I can put a 1 multiplied by anything. So like I was saying, one of the sections is only going to give you equations and ask you if it's growth or decay. So you're just going to look at that number that has the exponent, and if it's bigger than 1, it's growth. If it's less than 1, it's decay. So this is growth. And growth means that as you move from left to right, it's going to go up, 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 up. This is the only thing your graph can look like, guys. It won't it's not going to look like that. It's not going to come down like that. It's not going to go the other way. It will start out flat. It will start out flat, and then it'll go up, up, up. So we're going to graph our couple of points. And then there's one more thing that I want to point out to you. So 1 is the initial value. That means when x is 0, right here at the y-axis, we're going to start and put our first point at 1. I'm going to zoom this in a little bit. We're going to put our first point on 1. And that comes from this starting value right here. We know that it's growth, so don't draw this, but it's going to look something like this. Something like that. What we don't know, sometimes things grow really slowly and they can be flat like that. Sometimes they're growing really fast and they can come and turn and be really steep. So that's where plotting points comes in, is it gives us an idea of where to draw that, how steep to draw that curve. So you're just going to use your calculator. I'm going to plug in one negative number for x. So you could use -1 or -2. And we're going to plot points. So if I put -1 in for x, remember you get to pick this 2 to the -1, and you're going to use your calculator. Hopefully you have a real calculator and not just your phone. If I plug that in, then what do I get for y? If I type this into the calculator, y equals 1/2. If you pick something like -9, you're going to get a decimal so small, it's not going to work. So try to stay kind of like within 1 or 2. So I put -1 in for x. That's my x coordinate. I chose that. And when I plugged it in to find y, I got 1/2 for y. So that gives me an ordered pair. That gives me a point on the graph. -1, +1/2. Now, my hint, use the initial value. We did that. 1 positive and 1 negative x. So I'm going to plot a second point over here. Again, don't go too far out. If I do 2 to the 5th, that's 32. That's not going to fit on my graph. So I'm going to stick to like 1 or 2 or 3. I'm going to stay kind of close. Let's do 2. So I'm going to pick x equals 2. All right, and so I plug the 2 in. I put the 2 in for the x. 2 squared is 4 times 1 is 4. So when I put 2 in for x, I get 4 for y. That gives me an ordered pair. That's a point on the graph at 2, 4 right here. Now, I get a lot of kids that'll try to make a straight line there, or they'll even go like this and just kind of quit. Your graphs go on in both directions. So you need to complete the rest of the graph. This side needs to be flat, flat, flat like that, and it would have an arrow because it would continue going forever. This side needs to go up, up, up. Just try to make it a really nice, gentle curve. So this would be a great point for you to pause the video pause the video and try B. See how much of B. You might not be able to do the whole thing, but maybe you can get part of it down and then resume the video if you get stuck. Or if you can do the whole thing, resume the video to check. Okay, so I'm going to look at this number right here, this 1/2. That is my b. And since it is less than 1, it's smaller than 1, this is exponential decay. There's only going to be half of this whatever there is each time. It's going to get cut in half. 4 is my initial value. 4 is the a. So I'm going to start on the y-axis. I'm going to start at 4. Okay. And since it's decay, it's losing value. So it's going down, down, down. But then remember, it flattens out because we have to have that nice kind of curve shape. It's kind of like a 90-degree that you like curve at the corner. So I'm going to put a negative in. I'm going to pick a number, -1 for the x. You could use -2. If I put -1 in here, I'm going to plug that into my calculator. 4 times 1/2 to the -1 should give you 8. So -1, 8 is a point on my graph. -1, 8 is a point on your graph right there. So there's my initial value. I plotted one negative point, and now I'm going to plot 1 point on the right-hand side, on the positive side. So now I'm going to pick a positive number for x. How about +1? And if I plug that in, I get 4 times 1/2 to the +1, that is 2. So the point, my graph passes through the point 1, 2. The other thing, if it keeps getting cut in half, notice how it started at 8. And then as I move over, now it goes down to 4. And then as I move over, now it goes down to 2 because there's only half as much each time. So that's another way that you can plot points. I go over again, there's only going to be half as much. So half of 2 is 1. If I move over one more time, I'm going to go in half again. So I'm at a half. So that's another quick way to get points without having to plot them. If we apply that over here, your growth value is 2. So every time you go over 1, it's twice as big. So if I went over 1, it would be at 2. And then I double it again. I go over another one and I get to 4. If I went over another one, dang, my graph is pretty good. Be impressed, be impressed. Okay, so here's my graph. If you only plotted those 3 points, don't stop there. That is not your exponential graph. You need to keep it going. So we need one side to go like this, and the other side we need to have flatten out. Mine kind of came back up. It shouldn't do that. It should flatten out. So I say this, please know that there are other things, like even in example 2, we're going to do some other things to the graph that would change it. So this initial value is not always the y-intercept, because sometimes we can put other numbers that will shift the graph around. For the ones that we are asking you to graph, we won't put other numbers in there, so that will be where you start. So this next section, we're describing transformations. Okay, and we could kind of expand the, hang on, I can't talk on right. Oops. So we could expand the formula to look like this with transformations. And the cool thing about transformations is it doesn't matter if you're doing what kind of graph you're doing, they affect the graph in the same way. So whether it's absolute value or square root or exponential or parabolas, these h and k always have the same impact on the graph. If it's a negative in front, so like this one, that reflects your graph across the x-axis. We did the same thing with, hold on. That was the same with parabolas. And what that really means is like you flip it over. So instead of going up this way, it would flip it over and it would go down like that. If there's a number added or subtracted at the end, remember at the end, just like when we did parabolas, if it's after the exponent and the b, if it's something added or subtracted, that moves your entire graph up or down, shifts the whole graph. So since this is -4, it shifts down 4. I don't know if delta has any where there's a number in front, or if I don't know if you have to do that. If there's a number in front, that's a stretch. So if it's 2, means it's going to be twice as tall. So that's a vertical. You might not have that one on delta. Stretch of 2. And then if there's a number with the x. So when we did parabolas, if you had like x minus 2 squared plus 3. The number that's added or subtracted at the end shifts it up and down. The number inside shifts it left and right, but remember that it's the opposite of the sign. So this plus 5 in here is actually going to shift it left. Because x, if you're trying to make this 0, x would be -5. So it's actually shifted left 5. So if you want to take this and put any notes on it, those are the 4 transformations. Reflected across the x-axis if it's negative in front. If there's something added or subtracted, that shifts it up or down in the direction of the sign. Since this is a negative, that's going to go down 4. If there's an initial value, a number in the front, that's a vertical stretch. And finally, if there's a number in the exponent with the x, added or subtracted in the exponent, that shifts left and right, and it's opposite of the sign. So since this is plus 5, it's going to be shifted left 5. Okay, and now we get to word problems. Exponential growth and decay. So these are used in science. These are used for like half-lives, like when they do carbon dating and stuff, but also really frequently used in interest rate kinds of problems. So this is the equation. This is the exact same thing we just did, except that this is your b. So there's your a times b, and then they change the exponent to a t so that it stands for time, but it's the same as having an x up there. There is no difference. So that's the exact same formula. Here's the catch, and this is the part that people really struggle with, is you have to figure out what that b is. So right here, b, let's get a bright color. B is the 1 plus or minus r. R is your interest rate that you have to change to a decimal. If something is increasing, then you would add that rate to 1. 1 keeps it exactly how it is. If B was just 1, the value of it would never change. So if I bought a car, it would never change. So if your, whatever it is, like your savings account, if it's increasing, you're going to add the rate to 1. If something's losing value, like you buy a car and now it's worth less than when you bought it, that's decreasing in value. We also call that depreciate. Then you're going to subtract that rate from 1. So R is the rate, and remember B is the factor, the growth or decay factor. So that's a super common sticky point for people. Okay, so we're going to practice writing some equations, and then you would plug them into your calculator to evaluate. I'm not going to do that part because I don't want you to sit here on a video while I type in the calculator. So new car is purchased for $17,300. That is your A. That's your initial value. The value of the car depreciates. That means we're going to subtract from 1 at a rate of 9.25. That is a percentage. We need to change that to a decimal. So remember to change a percent to a decimal. We move the decimal place over 2 times to the left. So I would get 0.0095. And then it says, what will be the value of the car to the nearest cent after 15 years? That is your t. So if I plug this in, I get y equals, A is my starting value, 17,300, times, in parentheses, 1. So you always start with 1. 1 keeps something the exact same value it is right now. Since our car is losing value, we're going to subtract the rate, 0.0095 to the t. Okay? So you can, if you want to type this into the calculator just like this and put a 15 up there, you can. Or you could simplify that. So 1 minus that is 0.9905. And then t, the number of years, is 15. So you would type that into your calculator and figure out how much your car will be worth after 15 years. Our second example, a town has a population of 12,000. So that is our starting value. We're going to start with 12,000 people. And then, that's your A. It's growing. So now we're going to add the R. And the rate is 3%. We need to change 3% to a decimal. So right now the decimal will be after 3. I'm going to move it once and twice to get 0.03 is my R. What will the population be after 7 years to the nearest whole number? Make sure that you're paying attention to what they round to. Okay, like we're not going to round people to a decimal. Money you could. So Delta will mark you wrong if you don't do it right. And that was the source of much frustration. I'm just going to rewrite this so I don't have to scroll up. Okay, so y equals, A is 12,000. That's how much we're starting with. Times 1. We always start with 1. Since ours is growing or increasing, I'm going to add our rate, 0.03 to the t. So if I simplify that, 12,000 times 1.03, t is time. T stands for time. How many years? It was after 7 years. Let's see if I can do this one. So y equals 14,579 to the nearest whole number. Okay, this one is kind of backwards. This one, I gave you the equation and you're going to have to figure out the stuff. So we purchased a car. Oh, I did that one kind of weird. Purchased a car for 24,000. Here's the function. Okay, so obviously this is in thousands of dollars. This function can be used to model the value of the car in thousands of dollars. There it is. After X number of years. Is this exponential growth or decay? So remember your equation is A times B to the X. Which of those numbers represents your growth or decay? That is your B. So 0.8. Since that number is between 0 and 1, that means that this is decay. If it's less than 1, it's decay or losing value. If it's greater than 1, it's increasing in value or growth. What is the rate? Okay, so go back up here again for a second. Remember that B is this final number, right? That is not your R. So 1 plus or minus R is your factor. So 0.8 is B. That is your decay factor, not your rate. So if I started with 1 and R and got 0.8, right? That means I had to subtract something from R. We have to decide if it's plus or minus R. Since 0.8 is smaller, I clearly subtracted something from 1. You can reason through it. You could actually move the R over and subtract 0.8 and solve for it. R is 0.2. What is that as a percent? 0.2 as a decimal is 20%. What does that mean? That means that every year your car loses 20% of its value. So it decreases in value by 20%. So if you bought a $10,000 car, it loses $2,000 every year. Well, I shouldn't say that. $2,000 the first year. And then use Desmos to graph the function. What does the y-intercept represent? I think you already know that, right? The y-intercept, the 24, that's the initial value. When will the value of the car be 5,000? So if this is in thousands of dollars, this represents 24,000. So you're going to graph it on Desmos. It starts at 24. It's going to come down like this. That's going to be what your graph should look like. This is in thousands. So you're not looking for 5,000. You're looking for when is it 5. So 1, 2, 3, 4, 5. You'd look over here and go, how many years did it take? These are your years down here. How many years did it take until my car was worth $5,000, which is 5 on the graph? So we can go over that one in class, and I'll actually pull up Desmos and I will show you that one.